Hello, everyone. I'm Gabriel Hoerning. I'm a master's student at the University of São Paulo. So in this presentation, I'll be talking about the simulations and validation of the Commander3 code. This talk will compile some of my own results as well of the results of other students. So then here I'll be talking about on behalf of Eric from University of Fazlu, the PhD student Fazlu from Indian Institute of Astrophysics, the PhD student Yuyang from University of California, Berkeley, and the master's student Tamaki from Tohoku University. Okay, so about the motivation of this talk. The proposal here is to validate the Commander3 code routines in the sense that to check that they are unbiased and to check that the uncertainties are well estimated. We would like to run and install the Commander3 code in different clusters and places in the sense that it's find the possible problems which people could have during the procedure, like compile errors or version incompatibilities. And yes, in this sense. And I started to work with the Commander3 code and the team led by Maxine and Professor Hans Christian in March of 2022. And in this talk, I will be presenting to you some of homework results reached by me and the other members of the team, which contribute as evidence to validate the proposals above. Okay. Okay, about the Commander. With the Commander, we can do statistical analysis of CMB and microwave observations. It's a consistent framework to do this. And one of its main internal methods are the MC methods, which in this case is the Gibbs sampling, a very fast sampler when dealing with conditional probabilities. And to proceed with the code, we have to put information about a certain quantity, which can be a CMB map or a TOD. And the code will simulate other samples of this quantity in particular by making use of the MC method. The team from the University of Oslo offered the component separation course, which is highlighted here, to teach about the component separation methods used by Commander3 and how to use the code itself. I by myself didn't do the course, but my colleagues did, and so I'm learning about the routines and the physics of the code with the professors and the colleagues in the team. Now about installation and run. To install and run the code, we have followed some instructions and steps, which is available on Commander's component separation course on GitHub. And there were no big issues to install the code, just some normal errors, just like compilers, versions. But in the end, everyone was able to accomplish these steps in their available clusters. About the runs. The proposal of these tests we have been doing, as I said, it's to validate the code. But in order to do this, we have to put some information in the code to do. And the information about CMB and TOD we have been putting here, it's about the 30 gigahertz data from CMB, since we are interested in studying this in the Planck experiment context. So by putting this CMB and other noise data I'll be showing next, and TOD components, the code will produce the posterior data. So to do the statistics here, we are aiming to have around 1,000 samples per chain from the MC. So we put a map from CMB, and then the code will generate 1,000 more CMB maps, which we'll be using to do the statistics. The same for the noise and TOD components. We have run the code in several clusters around the world, which I'm showing some examples right here. So Tamaki, myself, Yuyang, Maxine, and Fazlu, we have run this on our university personal or national clusters. And of course, the difference between the number of cores you use and the kind of cores will vary a lot. The amount of days necessary to run the 1,000 samples in the chain. But what really matters to run the code is the amount of memory you have available in your cluster. So since you have the necessary memory, which is about of 200 gigabytes in the RAM, you will be able to run the code in more or less days, depending on the number and the kind of course you have. Talking about our own work results. Okay, so right here we have the input map, which is the map base used to generate the MCMC chain. And these simulations are for just 1 year simulation. They don't have the foregrounds here, but they have the dipole of the CMB. EQ and U, of course, are the Stokes parameters. And this is the first line. The mid and the bottom line are the mean and the standard deviations over those 1,000 samples we generated. So the mean of the 1,000 maps will generate this midline, and the standard deviation will generate this bottom line. Which in this bottom line, we can see the scan strategy of the telescope, since of course these blue areas where the telescopes passed by more times than the others has an error minor than compared to the other areas. Using this, we can build some histograms about the deviation of the samples, right? So here I'll be showing histograms in blue of the errors by using the posterior mean, the input, and the posterior standard deviation, as I showed you before. And in blue, the bars, and the blue bars, we can see the histogram of the distribution. And the orange line right here, we can see that we have a Gaussian distribution with mean 0 and standard deviation equals to 1. This is indication of validation of the code, because right here we have the sense that we can understand the uncertainties. So the deviations of the maps are well measured in the reconstruction of the maps. We can also do this for the correlated noise maps. So same as before, we will have an input map where we insert the Stokes parameters components as input. We will generate 1,000 samples and take the mean of these posterior maps, and also for the standard deviation. This is also for 1 year simulation. And doing the correlated noise histograms as before, we will achieve the same Gaussian with mean 0 and standard deviation 1 as we achieved it before. Just another example about TOD maps. The logic here follows the same as I did before, as I showed before. We have the posterior mean right here, and the standard deviation map, also highlighting the scan strategy. Now, talking about the reconstruction of the game, this is very interesting to see how good the code can recover the game. In this chart, you can see here the 4 radiometers, the 27M, etc. And in this left graph, this red line is the input gain, by is the input gain. And in blue, you can see the gain of each interaction, which is the same as a sample. So we can see long correlation lengths in this chart right here, but this is happening only because we are only using the 30 gigahertz data on these simulations. But in the left plot, oh sorry, in the right hand side plot here, we can see a comparison between the gain per PID of the input and the posterior mean compared with each other. So the red is the input and the blue is the posterior mean. We can see by eyeballing that they are very close to each other. But of course, we need a statistical metric to say that this fit is good. And here we have the deviation of the gain by PID in the left plot, and we can see that the deviation of the gain isn't bigger than 2 in almost all the PID. And by doing a distribution of the sigma, we can see that we are almost inside of 2 sigmas in error in this right hand side plot right here. So this is a good indication that we are recovering the gain, and by that, this is indication that we don't have any systematic bias or in one direction or another. Well, the conclusion of these on-work runs is that what is important to run Commander3 code is how memory you have available, and the Gaussian mean 0 and standard deviation 1 and our fits are evidence that uncertainties are well estimated, and the recovery of the gain, it's an evidence of no bias presence. And well, this is a work in progress. We have more analysis to be done to check other aspects of the code. We'll be doing next. Thank you all.